Hello and namaskar, friends. Welcome back to Pal Talk Machine Learning, the podcast where complex algorithms become easy conversations. I'm your host, Dr. Chinmoy Pal.
And I'm Ria. Today we are going to explore something that's both elegant and incredibly useful: Principal Component Analysis, or PCA for short. What is PCA?
Let's start with a simple question. What happens when your dataset has too many variables, maybe dozens or even hundreds of features?
Well, your model might struggle. It becomes computationally expensive, hard to visualize, and worst of all, might suffer from something called the curse of dimensionality.
Exactly. PCA helps us solve that problem. In simple terms, principal component analysis is a dimensionality reduction technique. It transforms your original features into a new set of variables called principal components, which capture the maximum variance in your data using fewer dimensions.
Why use PCA?
PCA is very useful when you have high-dimensional data, like in genetics, image processing, or finance. When you want to visualize your dataset in 2D or 3D, you want to reduce noise or redundancy in your data.
Or when your model is overfitting due to too many correlated features.
And remember, PCA is unsupervised, meaning it doesn't care about output labels. It's purely focused on how features relate to each other.
How PCA works step by step.
Let's break it down into steps. Standardization. First, we scale the data so each feature has a mean of 0 and standard deviation of 1. Covariance matrix. Then we compute how each feature varies with every other feature. This is the covariance matrix. Eigenvalues and eigenvectors. From this matrix, we find eigenvalues and eigenvectors. These help identify the directions or principal components in which the data varies the most. Sorting and selection. We sort the eigenvalues in descending order and select the top k components that explain the most variance. Projection. Finally, we project the data onto the new axes formed by these selected components.
Beautifully explained, Ria. So essentially, PCA rotates the axis of the data in a way that compresses it while keeping the maximum information.
Key concepts.
Here are a few terms you'll often hear with PCA. Explained variance. How much of the original data's variability is captured by a component. Scree-plot. A graph of eigenvalues to help decide how many components to keep. Loading scores. They show how much each original variable contributes to a principal component.
And yes, the first principal component captures the most variance, the second captures the next highest variance at 90 degrees to the first, and so on.
PCA in practice.
If you're using Python, PCA is part of scikit-learn. Just import PCA from sklearn.decomposition, fit your data and transform it.
In R, you can use the prcomp function. Also, visualization tools like bioplots and screenplots help you understand PCA outputs visually.
Real-life applications?
Here's where PCA shines in real life. In face recognition systems like eigenfaces, in stock market analysis to find patterns in price fluctuations, in healthcare for gene expression data analysis, in IoT and sensor data where you get hundreds of time series features, and even in image compression and noise filtering.
I've also used PCA in academic research to pre-process data before clustering or classification. It really speeds things up and makes models more robust.
Limitations of PCA.
Of course, PCA is powerful, but not perfect. It's linear. It won't capture nonlinear relationships. The components are not interpretable in terms of original features. PCA is sensitive to scale, so always standardize before using it. And it doesn't consider target variables since it's unsupervised.
Also, if you reduce too much, you might lose meaningful information. So always check the explained variance ratio before selecting components.
PCA versus other techniques?
Some alternatives to PCA include TSNE and UMAP for nonlinear dimensionality reduction, LDA, linear discriminant analysis for supervised dimensionality reduction, autoencoders, neural network-based compression.
But PCA remains a classic and trusted tool for quick, reliable pre-processing and visualization.
Final thoughts.
So friends, the next time you feel overwhelmed by high-dimensional data, remember, PCA is your ally. It helps you see the unseen patterns, simplify complexities, and make your machine learning journey smoother.
Well said. That's a wrap on today's episode of Pal Talk Machine Learning. If you found value in this discussion, do share it with your fellow data enthusiasts and researchers.
And don't forget to follow us for more practical and easy to understand machine learning insights. Until next time,
Keep learning, keep exploring, and keep it statistical.